Hi, welcome back to the Nav Station. I'm Andy Howe. Here at the Nav Station, our goal is to get you confident enough to head out on the water, turn off your GPS, and get to where you're going using celestial navigation. Here we are at the final problem. In the previous episodes, we've explored theory, we've corrected a site going from the raw sextant data to what we call our altitude observed. We've gone in the Nautical Almanac to extract GHA and declination for the body. And finally, we've gone into the site reduction table to get the calculated altitude and true bearing to the sun, the ZN, what we would have observed if we'd been standing at the assumed position. And then we plotted it all onto our universal plotting sheet. In this episode, we're going to put it all together in one quick episode to cover a full problem from start to finish. We're going to get it all on this piece of paper, and at the end we'll do a quick plot as well. So let's get started. Here's the basic information for the site. We've got our date, our Greenwich Mean Time, our Sextant altitude, designated this as a lower limb site of the sun, our index error, and our height of eye, as well as our dead reckoning position that we pulled off the chart. The first thing we're going to do is correct the site. So we'll start off with our Sextant altitude, HS, of 5605.2 minutes, and we'll apply our index correction. Index correction is nothing more than the index error with the sign reversed. The error is negative, it's off, so we're going to put the error back on. And next, we'll take care of the height of eye with our dip table. And the dip table correction is inside the almanac on the first pages. And I will say that a 10-foot height of eye is sort of a universal, what I like to call yachtsman's height of eye. It's a round number, it's easy to remember, and it fits a lot of situations on many small boats. So the height of eye correction for 10 feet, the dip correction, is minus 3.1. And we can find that in the table as well. Which leaves us with our apparent altitude, our HA, of 5603.3. Next, we go into the altitude correction tables for the proper month, August. And again, look under lower limb and find two values under apparent altitude that bracket our value here. And we pull out a correction to the right, and we see the correction is plus 15.3. And then that's going to yield us our observed altitude of 56 degrees, 18.6 minutes. And we can set that aside for later when we come out of the site reduction tables with our HC. Next, we go into the daily pages of the Nautical Almanac to find the GHA and declination. And we go into the box that has August 20th, 3 dates on each page, and slide down until we find the 18th hour of that day. And we read the GHA for 18 hours as 89 degrees 11 minutes. And while we're there, we keep reading across and we find the declination for the 18th hour of that day is north 12, 11.5. And before we leave the page, slide down to our little d value at the very bottom of the declination column, and the little d value is 0.8. And declination is showing that it's decreasing during the day as we go from one hour to the next, so little d has a negative sign. Next, we go into the back in the increments and corrections pages and find a box with the 21st minute And in that box, we slide down till we get to the 16th second, and under the sun or planets column, we pull out the GHA for 21 minutes and 16 seconds, which is 5 degrees 19 minutes. Going to add those together to get our final GHA value. But before we do that, let's slide over across the double line in that same 21-minute box to find the V or D in the corrections columns. Find a little d of 0.8, and we see that the correction is minus 0.3, which gives us a final declination of north 12 degrees 11.2 minutes. Now adding up the GHA, we get a GHA value of 94 degrees 30 minutes. We're almost done here with our required entering arguments for 249, the site reduction tables. Now we have to apply our local hour angle calculation. We have to apply our assumed longitude. And our assumed longitude is west. So according to the formula, LHA equals GHA minus west longitude. We're going to be subtracting our assumed longitude here, and we're going to put 60 minutes in the box, and then we're going to change 42.6 to 30 so that our subtraction ends up with 0 in the minutes. And that gives us a final LHA of 34 degrees. Now, if we wanted to, we could just do a short little diagram here. Let's do here's our LHA diagram, with this being the North Pole, this being the Greenwich Meridian, and here we are at 60 degrees over here. And here's the sun at 94 degrees. This is longitude, this is GHA, and this is LHA. So it's a relatively small number, so that fits the math that we did. The diagram looks okay, and we can move on. Next, we're going to go to the site reduction tables themselves. And we're going to enter on a page with our assumed latitude. We'll have to figure out our assumed latitude. We're just going to round off our dead reckoning latitude to the nearest whole degree. And while we're here, we'll put the assumed longitude up here as well. So we have an assumed position all set. So we're going to find a page set that has 12 degrees of latitude on it. And then we're going to find a page set that still has 12 degrees of latitude, but has the lower range of declination, the 0 to 14 range. And finally, our names are the same. Both the latitude and the declination are labeled north. So check that you see that you're on a 12-degree page still, the lower range of declination, and same name. Once we do that, we're going to pull out the HC, the D, and the Z. The column is 12 degrees of declination. The row, which will be on the left, is a 34-degree LHA. When you do that, you pull out 5646, and a little d of +3, and a z of 0.86. Now let's remember how this works. We'll draw a simple triangle here. Here's the North Pole. Here is us. The body is a little bit to our west. So the tables are going to give us this interior angle, which is going to be over here. But we don't measure true bearings that way. So we're going to be converting our Z to a ZN, which is measured this way, just like you would for a compass. So ZN equals 360 minus Z, as it says up in the upper left-hand corner of that page. LHA less than 180, ZN equals 360 minus Z. And here's the diagram to show that North Pole, us, wherever we are, and then the body is just a little bit to our west, only 34 degrees, so the triangle is flipped over that way. It's an afternoon sight with the sun to our west. So when we go into table 5, first we got to subtract our 086 from 360. So our ZN is 274. That makes sense. We said the Z is going to be a short distance over here, but the ZN is going to be all the way around this way to measure 274. So when we go into table 5, corrections to tabulated altitude or HC, we're going to find our minutes of declination that we haven't used, 11, and we're going to use 3 as the little d factor on the other axis, and we're going to find a correction of plus 1. And that gives us a final HC of 56 degrees, 47 minutes. Finally, we're going to take our HC value and compare it to the HO value. HC being the angle we would have recorded on our sextant if we've been standing at the assumed position, and that's 46.47. We were somewhere where our sextant read 56.18.6. So if we go towards, our angle should have been larger, but we started at 56.47 and we ended up at 56.18.6. We went away. So the difference between these two is 28.4 nautical miles away. And that's how we're going to plot. We're going to plot the assumed position. We're going to draw the ZN line in the direction of 274, and then we're going to start at the assumed position. We're going to measure 28.4 miles away from that ZN line, and that's where we'll draw our LOP. And we'll do that in the next segment of this episode. But before we do that, I just want to mention a little bit about this. Now, normally I don't draw diagrams for each site reduction unless I'm really confused or tired and I need to just have a reminder of what's going on. But you can do that, it's helpful. But the important thing is to note that we've got discrete blocks of information here. We've got our beginning information, we've got the site correction process here, we've got GHA and the LHA calculation here, we've got declination here, and finally we have the information that comes out of our site reduction tables and then the intercept calculation. Now, I like to just use a blank piece of paper. Initially, it might be helpful to you to set up a little form or a format, but the problem with a form is that there are a lot of other steps that are going to be plugged into the process, particularly when we get to the stars and the moon. And if you're not familiar with the steps, you'll be looking to stick something in those boxes or on those lines, and they may not even be applicable to the site you're taking. So you have to be careful if you use a form that you don't just automatically try to put something in every box, because it may not apply and it'll just screw things up at the end. So if you do use a form, before you start the process, X out or note the things where you don't have to fill in information, so you don't try to come up with an answer just because it's a blank space. But the short explanation is that all the information you do in a site reduction can fit on one page, and you don't need a lot of room. You don't need a huge piece of notebook paper to do this properly. You just need to be organized. You can set up blocks on your page so that the information makes sense as it's contained there. And things that go together, like information out of the Nautical Almanac, should be close to each other so you can double check it. And similarly, your site correction should always be one of the first things you do, and that will be separated from anything else. So the next stage of this episode is going to be a quick plot of the information. We've got everything we need to do a plot. We've got our intercept, we've got our ZN, we've got our assumed position, and that's all we need. And we'll set up a plotting sheet and plug those in and see where we end up for an estimated position of this particular site. Okay, so here we are at the plotting sheet for this final problem. I've already set it up with a mid-latitude of 12 degrees north, labeled the additional latitude lines, and a mid-longitude of 61 degrees west, and figured out where to draw the additional longitude lines. Down here in the longitude scale, I've scribed a line at 12 degrees, which is where we're going to pick off our minutes of longitude. I've labeled the important information for this particular plot over here. One would usually have it on a separate sheet and just be transferring that information from your worksheet to the chart without writing all this over here. So the first thing is to plot our dead reckoning position. This is something you would have already taken off of your chart so that you could do the site reduction. And we know that it's 12 degrees, 9.5 minutes north. So we'll set our edge of our ruler here at 9.5. And then we'll find the minutes of longitude down here, which is 42.6. So set one set of the dividers at 40, the other at about 2.6. And mark our dead reckoning position right there. The time of the site was 1821 GMT. Note that on this kind of a chart, a mile is essentially a fat pencil point. So you can only be so accurate with this, but it's certainly fine for the purposes of sailing a small boat across the ocean with celestial navigation. The other thing to note is that in terms of times, depends on what you like to do. I would not typically write GMT times down on my site. On my plot, I would use local times because that's going to relate much better to what's going on the boat. But for this exercise, we're going to write it in as a GMT time. Next, we find our assumed position. We know that the assumed position is along the 12 degree north line because that's where we had what we had to use to get into the tables. And our longitude is 60 degrees 30 minutes. So we'll find our 30 minutes on the longitude scale here. And here we have 60 degrees. Oops, lost it. And here is our assumed position for this particular site at 12 degrees north, 60 degrees, 30 minutes west. Next, our ZN line, our azimuth angle, our true bearing to the body, in this case, the sun. We need to find a bearing of 274 on our compass rose, which is off in this direction, and roll that up to the assumed position and draw in our dotted line that points to the body. Next, we're going to measure our intercept distance, which is 28.4. and we'll take 1028.4, and we'll take that distance, and we're going away. So we'll make a mark on the ZN line, that distance away from the assumed position. And that is where we're going to draw our perpendicular line of position, which is a bearing of 004 degrees, because that's perpendicular to our ZN. And that becomes our 1821 GMT sun, and we'll put a lower limb sun line there. So that becomes the line of position for this particular site at that particular time. Next, I'm going to take our line of position here, and we're going to find the closest point on the line of position to the dead reckoning position, which is right here. And at that point, we're going to draw in our estimated position. So we've labeled it as 1821 GMT, estimated position with the sun lower limb sun line symbol there as well. And then we would take this position as a starting point for our future dead reckoning positions and our course plot going forward. So let's write down the estimated position. So we have it. That is 12 degrees 06 minutes north, and just a hair over 60. So we'll call it 60 degrees, about 02 minutes west. And there we have it. We've got all the information we started with. We picked up an estimated position, which we would record in the logbook, and our DR plot would start from that estimated position, whichever direction we were going for the particular course and speed. And there you go. Now, typically, the assumed position and the ZN line are just construction lines and points, so you don't need to really emphasize the drawing of those. Initially, it's helpful to make sure you're doing things correctly, not measuring the wrong way towards when you should be going away, or you're totally off base on your assumed position. But eventually you'll understand that you just really need to draw those in lightly and then scribe your LOP, and that's really the important information you need. In a future episode, we'll look into plotting in a little more detail and get into calculating running fixes and a full day at sea where we're carrying this all the way through several hours. But for now, we'll stop there and move on to the next episode, which will be latitude at noon, the noon sight. If you haven't subscribed, please, down in the corner lower right, we've got a subscribe button. Click that. We'll send you alerts for future episodes. We do have several more episodes to go, covering all the other celestial bodies in the sky and some other situations. So we'll be rolling these out as we go through the next several weeks. So thanks for stopping by the nav station. Really enjoyed having you aboard, and we look forward to seeing you here next time. Thanks.